So hello everyone, my name is Igor Sikachina and I'm the reporter from Team Ukraine on the problem number 9, rail track divination. In this problem, we should estimate the distance and the speed of the approaching train using the sound information coming from the rails. And we should also estimate the precision and the accuracy of our method. I will structure my report in the following way. First, I will discuss the effects that take part in this problem, and then I will propose you a method of speed estimation, then we will come to the train distance estimation, and finally we will discuss the limits of applicability of our method. First, we decided to come to the rail station, from where we can clearly hear the knocks produced by the train going on the rails, and we should, using this sound propagating inside the rails, determine the distance and the speed of the train. And first we, of course, need to obtain the signal, and we do this by attaching the piezo sensor to the rails, and from which we can, using our Arduino board, obtain the information about the displacement of the rail and obtain the signal. And here's an example of the obtained signal, and we should understand what produces this signal, what are the sources of the signal. And we understand that there are multiple sources. First of the sources, one of the obvious sources is that when the wheel goes over the rail joint, it produces characteristic knock. And another, more or less obvious source is that when wheel during the exploitation wears off, and this phenomenon is well known due to the exploitation. Different defects occur in the rails, including the flattening of the areas, different holes, cracks, and such, which are discussed in different literature sources, and this indeed can produce a sound. And we understand that if we, for example, try at first produce a Fourier transform of our signal, we will obtain the following Fourier transform. But due to the fact that the Fourier transforms gives us a lot of information about the high frequencies and not the low frequencies which we are interested in, where the frequency of wheel rotation and the wheel knocks are, we cannot realistically use the Fourier transform to study this signal. And instead, we should study the time differences between different peaks. And we do this, of course, we understand that if we, for example, study the one wheel revolution, we expect that one wheel produces a periodical signal with a period of one wheel revolution, and multiple wheels produce a periodical signal, whereas the period of one wheel revolution will be the most prominent. And we, from our signal, obtain the position of all the peaks on the signal, and then we study the distance between each of the pair of the peaks to obtain a distribution of these distances, and we obtain the following distribution like this. So here is a period of one wheel revolution in sensor units, and here is the number of cases this period occurred. And we can see that on all such distributions from the real train, we observe a characteristic tower, which position exactly fits the speed of the period of one wheel revolution. Thus, we can use it to determine the speed of the train. To verify this, additionally, we wrote a program in Wolfram Mathematica to generate a periodical signal from wheels, and we can see that distributions of time differences is indeed similar, and the position of the tower characterizes the period of one wheel revolution. So we experimentally measure the speed of the approaching train, where one of our team members experimentally measured the speed of the train standing near it, and we measured the speed of the train at great distances from it, and if we use the correct radius of the wheel, we obtain quite a close result, and we can indeed measure the distance to the train. But if we don't really know the wheel radius, then we will get different results. So here you can see that if we use the proper radius of the wheel, we will get great results with an error of to about 2%. But if it happens that the wheel has a different radius, we will get an error up to about 30%. So now we can determine the speed of the approaching train. Now we'll come to another problem. We need to estimate the distance, and this problem is much more complicated. At first, if we can clearly hear the approaching train using a sound sensor, we can study the signal coming from the air and the rail, then compare these two signals, and determining the time difference between them, we can determine the distance to the train using this formula. But this method has clear problems. One of them is that sound approaching coming from the air is much different from the one from the rails, so we should process it in another way. And another problem is that the sound sensor is sensitive to any noises coming from the outside world, and that the sound sensor is not really applicable at great distances because of low train volume. So this method is not really applicable in real situation. Another solution would be to study two amplitudes, one at one moment of time, then after some period of time, measure the amplitude again, and using these two amplitudes, determine the distance to the train. And now, this requires that the attenuation function is not exponential, but we clearly from our experimental results see that the signal attenuates exponentially, and thus, if we try to use this method, we will get a result that we are not really able to determine the distance to the train because of the exponential attenuation. And our only solution is to estimate the initial amplitude the train produces while it's moving. And using this formula, if we estimate the initial signal amplitude, we can determine the distance to the train. So now, how do we estimate the distance to the train? The amplitude of the signal from the train. We expect that the amplitude is proportional to the momentum provided from the wheel, and we understand that in reality this momentum is dependent on the effective mass acting on one wheel of the train. And this effective mass, as known from the literature, reduces with the increase of train speed. Thus, we should account that into our problem to determine the initial signal amplitude. And also we have a gauge coefficient which determines how the momentum is translated to the amplitude of the signal, and it's different for different trains. We measured it experimentally for different trains. And now, how do we exactly determine the distance? We first take our signal, we eliminate the noise, and we determine the average amplitude of the signal, and then plug it into our distance formula. And additionally, we understand that using this method, we will get the distance, not the beginning of the train, but rather somewhere in between. So we should additionally account for the length of the train, which we also estimate. And finally, we are able to study the distance to the train. And we'll do this experimentally. We placed our experimental stop at the distance of 800 meters from one of our team members, who signaled us about the approaching train. And from this moment, we knew that this train is in reality at 800 meters. And then we iterated the position using the known speed of the train to determine the real position of the train. And also, we measured the distance to the train using our method as described in the problem. So we get the following result, where if we know the amplitude, the gauge coefficient, we can measure the distance to the train with great accuracy, but in fact we don't usually know the amplitude characteristic of the train, thus we will get a greater error. So if we know the amplitude characteristic of the train, we get an error of up to about 25 meters, and for unknown train our error jumps up to about 100 meters. So now we should discuss the limits of applicability of our methods. We understand that depending on the amount of information we have, we will get different results. So if we know about the wheel radius and the amplitude characteristic of the train, we will get a much better accuracy and precision for both speed and distance. And other cases also apply, but most commonly we know the wheel radius and we don't know the amplitude characteristic of the train, thus we can with great accuracy estimate the speed of the train, which is good, and with this accuracy we can estimate the distance to the train due to the fact that they may have different amplitude coefficients. And another thing is that we have limitations on the maximum distance we can measure the distance to the approaching train, because at some point the signal will attenuate that much that this sensor won't catch any signal, and thus we won't be able to study the signal. And thus for minimum distance is quite low due to the fact that it requires the train to be really close for the sensor to go over its limit of sensitivity. And also we have a maximum distance, which is about 1 kilometer for 10 meters per second moving train. And we also have a minimum speed of the approaching train, below which the signal also will be too low to measure the distance. And so it's about 3 meters per second for the train at the distance of 500 meters. So we finally come to the conclusions of of my report. First, we proposed a method of speed estimation, which is based on study of time differences inside the signal we obtain from the piezo sensor. And we can estimate the speed of the approaching train with great accuracy. And also we propose a method of distance estimation, which is based on estimating the initial amplitude of the signal. Thank you for your attention.
Once again, hello, my name is Shantanu Kadam. I am the opponent in this round, and I am with Team USA. And I would like to start by expressing, saying that the first two procedures that the that the reporter presented are both procedures that my team is in agreement with in regards to the concept of looking at the displacement and the change in the propagation of the waves through the air versus the track, which is the second method they proposed, as well as the first method in, or forgive me, it may not have been the first method, I apologize, in regards to the attenuation. One thing that there are 3 or 4 main things that I would like to discuss with you. And my biggest concern is in terms of the assumptions that you've made throughout your presentation, specifically in terms of when you go to actually calculate your using data and experimental values. So on that point, I am curious as to the sampling size and how many sets of data you took in each trial. Whether you had two systems set up at the same time or only one system, for example. And as well as how you would plan to calculate the velocity of the train if the rails were smooth, as opposed to having some sort of periodic indentation or connection in them. The other aspect that is of curiosity to me is, and that I'd like to discuss with you, is the types of wave propagation through the track and how you determine which of those was the most significant. It seems to me there are some types that you did not consider that would be perhaps meaningful to consider, as well as simply the construction of the rail itself, in the sense that there are different aspects to the rail. If you look at a cross-section, there's the rail head, there's the side, the underhead of the railhead, there's the side of the rail, and then there's the rail bed. And all of those will influence the dampening, the attenuation, as you mentioned, in different manners, and lead to different warping. So I would greatly appreciate perhaps understanding how you eliminated certain aspects and decided which ones are the most important. In addition, I'm sorry, was there some? Oh, I see. Currently, I don't want to plug this up at the moment. Thank you, though. In addition, I'd like to know a little bit more about the actual connection of your setup to the rail system. So I realize that was a lot at one time. The primary interest is how, first of all, how did you decide which type of waves you were interested in analyzing? Secondly, how did you actually analyze those through the connection to the rail, and how you determined what parts of the rail were important to analyze? And then third, how you could eliminate or maybe make your procedure more independent of the data points that were used, or of the assumptions that you made. And that is all that I have to say on this topic. So if we can move to the discussion.
You have to.
So, okay, you want to first discuss how different modes of oscillations and how the signal attenuates in regards for different modes, as I understand, because it can be used, as you said, to improve the results. In fact, yes, we studied different oscillation modes. We understand that due to the overall structure of the rails, it matters really. It changes the attenuation coefficient depending on which oscillation mode we look at. Mm-hmm. So we in fact understand that the oscillation mode of this mode, which is just damps with due to the damping inside the ties and the ground below the rails, that significantly increases the attenuation in that mode, and the mode that contains maximum information due to the fact that it attenuates much lower is this mode that goes along the rails. And yes, indeed, it would be really helpful to study this mode. But unfortunately, we faced a very important problem, because this means that we should place our sensor inside the rail joint. And the rail joints are positioned in area where we performed an experiment at the distance of 1 kilometer. That first significantly limits the amount of area we can put
that's
the
very
experiment.
interesting.
And another point, which is much more important in our case, is that if we place it inside the rail joint, we just will lose the sensor if the rail passes by, because the rail joint is most vulnerable area to place any sensor in. And also
is the sensor connected by a wire to the?
Well, as we discussed about the way how we connected the sensor. Yes, it's a good question. So we mostly studied the mode which goes perpendicular to the direction of the rail, but not into the ground.
Right.
So we attach it to the side of the rail.
We in fact also found this the most
Yes,
easy to measure.
it's the most, it's the easiest place to put the sensor and to measure the signal from. So that's why we are using it. Yes, it limits the distance, maximum distance. We can study the train as opposed to putting the sensor inside the rail joint, but we can do this and account for the different attenuation coefficient, and we'll get better results.
The reason I bring this up is because because there's so many parts on this train, including not just the wheels as you mentioned, but also the defects within the rails, the wheels, the connections, the torsion within the train itself. You have like not only the types of waves that you mentioned, but you also have like a torsional wave, and you have different deformations of the waves, not only up and down or forward and back, but also sideways and anti-symmetrically, which is why I was curious about that. But if we could move on briefly, one thing, in the problem statement itself, it does ask, in terms of the accuracy and precision of the measurement. And I was wondering, something you didn't measure is when is your procedure applicable? Are there certain frequencies above which you cannot use this data, or are there certain frequencies below which you cannot use this data?
Well, we have a limitation on the sensor we use, in fact, because the sensor should have a certain. So here's the device limit. We should have a certain data frequency reading rate. So it should be about greater than 1 kilohertz to be able to get multiple data points for one peak. And that's really important. And in fact, in reality, because of the material of the rails, the material properties, we don't really have a limitation on the frequency. Like
that's interesting. Okay, may I add to that real quick?
Yes.
So in terms of materials on the rails, did you consider the effect of the rail bed? Because above certain frequencies, including above those frequencies, it seems that from prior research that's been done in this field on these topics, that above those frequencies, the attenuation is significantly caused by the rail bed as opposed to the rail itself.
Yes, that's a very good question. So in fact, because we are interested in the total amplitude of the signal produced, we are not really interested in the frequency. We understand that the study of the frequencies will lead us to a more complicated problem because the different frequencies attenuate differently. So we try to make our method more universal to be applicable in different situations.
I see. I would actually argue that the fact that there are many different frequencies means that there are some frequencies which would propagate further. So the distance that you have placed, I think that you could actually find a larger range within which you could measure like how far away the train is.
Yes, indeed.
If you were able to calculate that.
If we additionally use a better sensor, we can indeed also study better the information coming from the train. So this is also a device limitation due to the fact its sensitivity, its frequency response, its
Sorry to stop the discussion here.
So, my name is Kirill Gerashenko. I'm representing the team of France, and I would like you guys to review the problem number 9, which is called rail track deviation. So the problem asks us, if we have a rail, we have to estimate, but depending on different parameters, we have to estimate speed and and distance. Okay. Okay, so go around. We can go. Thanks a lot. just excuse me for this problem. So go for the report. I will go for the summary of the report first of all. So I will go for a simple progression. First of all, we have to say that the all experience was working with the real trains, real rails. So first of all, we started with the speed estimation. Speed estimation, we have the sound of the rail. There is two possibilities that you proposed it as the rail join, and the second one, the time between two shocks measurements, and actually use the second one. And next one, we have the method verification. To use that, you use simulation, that we just discussed it now, and you use simulation. So you may, as I get it right, you have some assumption on the unstable, on is not ideal wheel. So we have this assumption, and this is how we can simulate all the possibilities, and you measure it, so we have verification of the frequency distribution. Next, you define wheel radius. So with the different wheel radius, you talk about different experience. Next, we have the position measurements. Okay, for the position measurements, you propose actually domain. So you started that you said you have to know the attenuation of your wheel, of your track, and next you would check the same thing times between two shocks, and you have estimation of opposites. So because opposition, we started that there is mention of the limits of the model. It was very good, this discussion, and also you started this discussion about hypothesis, what was built the presentation. Next one was mentioned dependence on attenuation over frequency, which is very nice because actually in the report wasn't any mention of the attenuation. Next one, they didn't. Some problem. We think that you didn't summarize the report, and there wasn't presentation, so it was very hard to follow you because all this good points was just in the discussion. And discussion was based on the different waves. Also, it was discussing the limits of the sensor, which is we get the 1 kilometer max distance what we know, and also very interesting different oscillation modes, and I think we can go to discussion just here. So
may I interject very quickly? There
yes.
were 2 points that I asked that you did not address. First of all, how would you calculate the velocity if this rail was smooth? And secondly, how long was your data set for each trial, and how many sets did you take in each trial? So what was your sampling size and length?
We were only really able to study, for the speed estimation, we were only able to study like one train passes through one of our team members, and he measures the speed of the approaching train and signals us to do the same. And we did this for 4 different trains because we should know the exact time they passes by. So, and we were also given the information about the number of carriages. So to be able to properly measure the experimental speed.
I see.
That's why we were not.
That makes sense. I think if you took 2 sets of data for each train, you would be able to actually determine without as many assumptions on the maximum amplitude as well as the velocity.
We have a big problem of getting 2 same trains going through the same track because we don't really regulate the.
I think you misunderstand me. If you take 2 data points at 2 different places on the train, that will give you 2 different delta times or like delta distances, and from that you should be able to calculate that. I have some theory here as well. If we have time, I can show that.
And I want to a bit clarify because I see that opponent and reviewer don't really missed the point a bit. The method about the sound sensor here in the train approaching is very, very poor and not really applicable, so we didn't use that. And another one we proposed, it was based about measuring 2 different amplitudes. And this method cannot be used at all because it just, this equation doesn't have a solution for the distance because there is no distance. So it's also inapplicable. So we estimated the amplitude of the approaching train, estimated one single amplitude, and measured the amplitude with our sensor. So we have 2 amplitudes, and we just use this equation to determine the distance.
Right, but this requires some predetermination of the system. And so what I'm saying is, if you were able to measure 2 different points and use maybe a concept of a Doppler shift, then you would maybe not have to do this. And that refers to one of your other procedures, but I think you could have tied that, or like maybe if you tied that together, or like
we also try to use different multiple measurements, but the real problem is as following: we can't really distinguish the heavy train at great distance from the very light train at lower distances because they produce a signal of the same amplitude. And even if we put 2 sensors, we just get the exponential attenuation, which doesn't care about the change of distance. It will just tell us that the train, it will get this method essentially with no distance.
Interesting. Do you think that has to do with like maybe not accounting for the parameter of mass and like the weight of the train? Because that definitely affects the as well as the density of the track itself.
Well, these parameters of course influence, but we about the rail information is stored in the attenuation coefficient, and the train information is basically stored inside the train length. This amplitude coefficient, this one, and the train speed, of course, and the mass too. So we can account. We don't really know the information about the approaching train. Like we should estimate the distance to the train without knowing what is the train.
I just put
so that's the problem.
Just to do the conclusion. So if I know I want to measure the speed of the sound and distance, what do you know about the train that you can measure distance and speed?
With most accuracy.
With just what? Yes, with most accuracy.
So the speed, we just should know the radius of the wheel, which will provide us the most significant information about the train. So that will be more than enough. We will get the precision of 2% and accuracy, or the precision of 1% and accuracy of 2%. So and about the train, we should know first its amplitude coefficient, so which is based on the amplitude of the signal produced by each wheel.
Yes.
We should also get information about the weight of each carriage of the train.
Yes.
And we should also should know the total number of the length of the train. And using all this, we'll get this result at best.
I have to say that if you have the question, you can go in and you can just join us. And if not, we just said about your amplitude definition, but we have to know the amplitude of each wheel. So can we? I would just propose to discuss that there was the model, which was that there is some not ideal wheel. And I would just ask the opponent, what do you think about this? If it's really like that, this is the real creation of the model, can we compare it? What is the error of this?
Oh, so you're asking about the feasibility of
yes,
simply looking at the wheel itself?
About model,
right. So I don't agree fully with this concept of looking at the wheel as the sole detector of information coming from the train. And one of the largest reason for that is because it requires knowing a lot of things about the train to begin with before you take your data measurement, which goes against the prompt of the question, which is if you're at some point or 2 points and you don't know much, how little can you know about the train and still end up calculating the speed and the distance?
Okay, it's just a really quick question. Why about model of the report? Why do you think it's not accurate? Why you think there is the problem? Where is the problem in this model?
Right, I think the problem is that they did not account for what the frequencies can be and what the maximum frequencies can be in terms of the wave numbers and the complex aspects of those, like literally the complex number aspect.
And do you think it's important or not?
Because of the fact we use the sound sensor and we observe that the simulation which just produces a periodical signal from different fields produces almost the same result of the signal in the time distribution. For us, it just means that that we essentially use pretty much the most information we can get because the sound sensor doesn't give us more information.
So we just experience will verify that this can work.
Yes, and about I want to additionally clarify about the defects on the wheel. Well, it's not only just the flattening of one area of the wheel. There are a lot of different defects that can occur, including the cracks, the fudges, the increase of surface area. All these effects will produce a signal which will have a frequency of 1 wheel revolution. So essentially, it just depends on the speed of the train. So we use this concept to determine the speed, and for the distance, we only left with just estimation of the initial amplitude because there is a lot of variety for the different train combinations. And well, if we even try to put even considering some specific cases where we assume that the train approaching has certain properties, we will just have a really complicated problem with just guessing how the train what the train should be to produce this exact signal for this exact sensor. So that's an insanely complicated problem. So that this is why
it is a complex problem. I will also say though that there is literature on this type of complexity, which is where my group got some of its initial starting point.
It's not like it's impossible, but it will leave us with a really complicated problem, which is not really probably solvable
just
in general.
Question just there.
Yes. Actually, I have to talk about your model for the wheel because you said there is kind of one hit on the wheel that produces a periodic signal, correct? So what if there are in fact more than one hit?
That's a very good question.
Then you would overestimate the speed actually.
So,
there is a hit
so
on each side.
you see, yes, we understand that one wheel may have multiple defects which will produce, for example, two different signals for one wheel revolution. And this case can be viewed as two different wheels with one defect, essentially. And studying and this essentially goes to the amplitude coefficient of the strain. So even if a strain has multiple defects on one wheel, we already account that in considering its amplitude characteristics.
But we have to consider amplitude characteristics.
Well, we use this amplitude coefficient to determine the distance of the train. We have to assume some value because for different coefficients we just get a shift of distance. We can't really determine due to the exponential attenuation. This is our biggest challenge.
We don't have the time. Just if you want to say something for this.
I have very little to say on this concept. I'm still waiting for an answer on how you'd calculate the velocity if the rail was smooth.
Okay.
Sorry. Nicola?
So if I understand correctly, you attached your microphone, it's not real microphone, but to the rail using Bluetooth.
Yes.
Couldn't that filter out some frequencies?
Yes, that's also a good question, but we just had to use something to attach the sensor to the rail because the rail surface is very rough. So we had to use some kind of material that will just flatten it out. And well, the blue tack is just suggested material to thin blue tack layer helps to attach the sensor, and additionally. Yes, it may change the amplitude response, the frequency response, but it didn't really change the results because we're still obtaining the signal and it still correlated well with CC.
From our experimental data, we found that also certain types of tape with certain properties work well, such as duct tape, for that in case in future experiments you want to try that.
Yeah, so you said you have tried with one piezo, but also with more than one piezo on the rail, right?
You mean
one detector, one sensor on the rail?
Yeah,
you check with only one or also with several?
We tried to use several sensors to study the signal, different signals, and try to measure the distance
at the same time,
from this information. That was one of our basic assumptions to detect the distance, but then we just saw that the signal attenuates exponentially, and it just provides no results about the distance. However, yes, it can be used to determine the speed. As in the same way, we can use it to determine the speed in case of one sensor, but waiting some time. But it has lower accuracy than the method we proposed.
But do you think if you put one sensor in each wheel, you will have a better result?
At each what?
So you use one sensor attached on one rail, right?
Yes.
And my question is, if you use two sensors, one sensor in each wheel, so what will be the difference?
Well, we will get, of course, different signals due to attenuation, but for the speed estimation it will matter at all just because of how the signal is structured. And for the distance, we again just don't really obtain the information about the properties of the train due to all the signal attenuation processes. This information is just lost.
Okay.
That's the problem.
Okay, so let's assume that you know absolutely nothing about the train. You don't know the mass, the radius of the wheels. What is your real accuracy in that case on the speed and on the distance?
If we use a realistic range for values, we'll get this result for accuracy and precision. So the precision of both the speed and distance estimation are more or less the same due to the method we use, but the accuracy suffers greatly from these cases. So this is for realistic cases, ranging from the light train without any load and just one cart, just to some other completely opposite case, really long train with heavy load. This gives us the following result. of course, we may consider different, more exotic configurations like 10 wheels in the row and such, but this is not a typical case for the train structure anyway. So this for realistic conditions.
Sonia?
Yes, I have curiosity about your experimental measurements. How much time it took you to get
So to get the speed estimation and the distance estimation, we need to study the time period of multiple wheel marks.
Over which was the timing? Okay, weeks, months, days.
You mean of our experiments?
Can clarify with the next. This is to bring to me to the question to everybody. Do you think that the environment can change your results?
Environment.
You were talking about the train, the rail, and what about if you succeed to have a good object, a device, you can estimate everything, and you put and okay, the environmental conditions change?
Yes, that's a good question. We studied the train in about one season, so the temperature was more or less the same, in the same range. But in fact, yes, indeed, the rails change their attenuation coefficient and their length based on the temperature, which will change the attenuation coefficient and change. But the change is not that significant compared to other problems for the distance estimation. Mm-hmm. And the speed estimation will not suffer at all because it doesn't care for the properties of the rail.
What about the device? You take the measurements.
Oh well, it changes the frequency response. It should change the frequency response. But from the documentation, it's not really clear if it will suffer greatly from even the rain. So it just measures the pressure produced by the rail. So it isn't really based on the, for example, humidity. The temperature, yes, basically changes the frequency response, but the amplitude we get will be pretty much the same.
Shantano, if you want to clear.
Thank you. I greatly appreciate that. One interesting extreme case to consider is if there is a bend in the rail right before you come into the track. And in exploring that case, you kind of see what is a more general approach as opposed to maybe some of the ideas mentioned here. Because what previous studies done in the field have shown that, and I do have a link to these papers if you'd like to see them. But previous studies have shown that when you have the curve, the attenuation and the wavelength traveling within the two rails will actually become stronger on one side while it becomes weaker on the other. So if going back to the other question, I suppose, if you put a detector on both sides inside the rail, you will actually see a inverse relationship between both of them. So I guess to answer one aspect, perhaps.
Sorry, the jury can now decide their marks.